Welcome back everyone to another video in our Fundamentals of Structural Engineering course. And in this video, we are going to learn about structural design of RC beams against flexure. As you can see here, if we have this beam that it is under the effect of P, which is a vertical force, this means that this beam is going to have a bending moment here in the middle of this span. And we have learned that the governing formula for the design of moment is phi mn, which has to be bigger or equal m ultimate, where mn is the nominal moment capacity of the section, and the phi is the reduction factor for the moment strength, while m ultimate is the factored load, which, as we have learned, could be obtained by multiplying the moment due to the dead load and the moment due to the live load per the amplification factor as per the LRFD load combinations. So how do we obtain these values? And we want to understand from where the equations of the analysis or the design are actually derived from. So here, if we cut a section in the middle of this span, it is going to look like this. We have this beam section. Here in the top part, we are going to have compression stresses, and in the lower part, we are going to have tension stresses. In the tension side, you know that we are relying on the steel bars to resist the tension forces, while in the compression part, we are relying on the concrete itself. This is because the concrete has high compressive strength, while it doesn't have a very good tensile strength. That's why for the tensile or the tension stresses, we are relying on the steel here in the lower part. Here you can see the strain graph for the compression part and the tension part. Here at the top you can see the maximum strain allowable for the concrete, which is 0.003, while here in the bottom you can see epsilon, which is the strain in the steel bars here at this point at depth D. So this is the strain of the concrete and the steel. What about the strength itself? Here you can see that we have this force, which is the tension force in this beam due to the area steel here, and here we have the compression force due to this area of concrete. The force here, as you can see, it is a concentrated force because it is only concentrated at the point where we have the steel rebars, and it is calculated by area steel multiplied by F field. This is the tension force inside this beam. While the compression force, as you can see here, it is limited by FC, which is the strength of the concrete, and it has this parabolic shape. It increases till it reaches this FC value, and it keeps decreasing till it reaches 0 at this neutral axis. This is the neutral axis here that we have. In this part it is compression, in this part it is tension. Here we have 0 stresses. As you can see here, we have 0 strain and we have 0 stresses. So this is the compression part. But actually this shape, this parabolic shape, it is hard to use it in our design or in our analysis because it is not a regular shape. That's why we need to convert it into an easier shape that we can use. That's why we are going to convert it into this shape. This is a rectangle shape, so of course this is going to be much easier to deal with. But here normally we had this C. This C is the depth till the neutral axis, this C. But if we are going to convert it into a rectangle, of course this depth is going to be less than C, and also this value here, it has to be less than the maximum FC, because we are converting this parabolic shape into a rectangle. That's how we came up with this shape here. Here this value, it is 0.85 FC instead of FC, which was here, and here this depth, it is A instead of C, where A equals beta 1 C, and this beta 1, it is factor that depends on the strength of the concrete. And I'm going to show you the table from where we can get this beta value. So now we understood the section, what do we mean by the neutral axis, the strain in the concrete, the strain in the steel, and the force calculation or the stresses calculation in the compression part, in the tension part also, and how we converted this parabolic shape into this rectangle shape. And now we have the tension force and we have the compression forces. So the next step, we know from equilibrium that the tension must equal the compression. So the tension force, which is area steel multiplied by F field, here it has to equal this force, which equals 0.85 FC multiplied by A multiplied by B, which is the width of the section. This width, it is B. So we have this equation of equilibrium, and from this equation we come up with A, this factor here, which we call it the depth till the neutral axis. Actually, it is not till the neutral axis, it is the depth of the compression rectangle itself, because we know that C is the real depth till the neutral axis. However, we have converted it into A now to be easier to deal with, because it is a rectangle shape. So A is going to equal area steel F field over 0.85 FCB, and this is the equation for the A. While the equation for the moment, Mn, here we have this section, we have here compression force in the center here, and here we have tension force at this point. So if we want to calculate the nominal moment, we need to calculate the moment due to this couple force, which is one force here and one force here. We can calculate it by calculating the moment at any point, either the center here or the center here. Let's calculate the moment at this center here. It is going to equal F field multiplied by area steel, which is here area steel multiplied by F field multiplied by this distance here between the middle or the center of this compression till here. And we know that the distance from here till here, it is D, and this part is A. So the distance from the middle till here, it is going to be D minus A over 2. And this is how we came up with this term here. And for this part, it's going to be the opposite. We will calculate the moment from here. It is going to equal 0.85 FC multiplied by A multiplied by B multiplied by this distance, which is A, which is D minus A over 2. And this is the equation that we have here. This equation, it is already available in the handbook. You just need, I just wanted you to understand from where we got this equation, but it will be already given. You don't need to memorize it by yourself. So how do we get phi, which is the reduction factor for the strength? We have learned here while we were discussing the approach of the code, we were discussing the reduction factors, that it is different between tension control section and compression control section and transition sections, and also for shear and for bearing. For tension controlled, it is phi equals 0.9. For compression controlled, it equals 0.65, while for transition sections, it equals this term, which is 0.48 plus 83 epsilon T, epsilon of the steel. So how do we decide, or how do we know if this section is tension controlled or compression controlled, and what is actually the meaning of this? If a section is tension controlled, this means that the steel is going to fail first before the compression or before the concrete in this section. And if a section is compression controlled, this means that the concrete is going to fail before the steel. In columns, for example, most of the columns are mainly axially loaded by compressive strength, so this means it is compression controlled sections. While beams, we want the beam to be tension controlled, because a tension controlled section is safer than a compression controlled section, because if the steel is going to fail first, it is going to give us signs. You know, the steel has pretty good ductility. It is not a brittle material like concrete. So if the steel is going to fail, it is going to start to first elongate. We are going to see cracks. It is going to give us some signs that there is something wrong happening. So we will have time to evacuate the building and to save ourselves before the collapse. While the compression failure, it is a sudden failure. That's why it is preferable to always have a tension controlled beams. In order to decide if this beam is compression controlled or tension controlled, here as you can see this beam, we have here the epsilon of the concrete, which is the maximum tensile strain for the concrete, which is 0.003. What we are going to calculate is the tensile strain of the steel. If it is bigger than this value, which is 0.005, this means it is tension controlled. If it is smaller than 0.002, this means now it is compression controlled. In the middle, this means it is a transition section, that it is not exactly a compression controlled or a tension controlled. So how do we calculate the epsilon t? It comes from this equation, which is Et equal 0.003 multiplied by d minus c over c, or 0.003 beta 1 d minus a over a, where beta 1 is the factor that we converted the c into a using it, as we explained in the first slide, and beta 1 we get it from this table here. For the concrete, which is between 2500 psi to 4000 psi, which is the regular concrete, and most of the time this would be the concrete in the exam, beta 1 equals 0.85. If it is bigger than that, you are going to use this equation or this factor to convert the c into a. And all of these equations and this table are already available in the FE reference book. Here, this is a summarized table for what we have discussed in the design of beams against flexure. First, if we want to obtain A, or the nominal moment, we need the section dimensions, the area steel, and the concrete and steel strength. We refer to the reference book equation, which is A equals area steel F yield over 0.85 FCB, or Mn equals 0.85 FC prime AB multiplied by D minus A over 2, or area steel multiplied by F field multiplied by D minus A over 2. And in order to obtain beta, we need the concrete strength, and we will refer to this table. We will get beta. If we want to calculate epsilon for the steel, we need the section dimensions, and we need the depth of compression, which is A, and we need beta 1. We know how to get beta 1 and the section dimension, and we know how to get A. We will refer to the reference book, this equation, in order to get the epsilon. In order to obtain the phi, we need epsilon, and we will refer to this table. And finally, we will solve for this equation, which is phi Mn has to be more than or equal M ultimate. Here, this is a summarized path for how we carry out our design. First, we need to get the A, and we need to get the M nominal. Using the FC prime, we need to get the beta 1, and here we need to obtain the epsilon in order to get the phi. Here we use this beta 1 to obtain the phi, and finally we can solve for this equation, which is phi Mn has to be bigger than M ultimate. So now let's have an example on this. As you can see here, the cross section of this beam is reinforced with 3 inches of steel. This is the area steel. FC prime equals 4000 pounds per inch square. This is the FC prime, and F field 60,000 psi. Assume that the tension steel yields at maximum moment. Most nearly, what is the area of concrete required to balance the steel force when the steel yields? So we want to calculate this area concrete. We will start first by the equation, which says that A equals area steel multiplied by F field over 0.85 FC prime multiplied by B. We know the FC prime, we know the area steel, and we know the F field, but we don't know the B, but it's okay because we want to calculate the area of concrete, which actually equals A multiplied by B. So A multiplied by B equals area steel multiplied by F field over 0.85 multiplied by FC prime, which equals 3 multiplied by 60,000 over 0.5 multiplied by 4,000, which is going to equal 52.95 inch square. So the answer is D, which is 53 inches squared. This is the closest answer. Let's have another example. According to ACI 318, what is the value of phi that should be used in the design of the beam section below? If we want to calculate the phi factor, this means that we need to understand first if this is a tension controlled or transition or a compression controlled section. We will start first by calculating A, which equals area steel, F field over 0.85 FC prime B. We have all of these values. We have the area steel, it equals 5.08 here, which is 4 of 10, number 10 bars. Here it is given the area steel 5.08 multiplied by 60 over 0.85 multiplied by 4 multiplied by 12. This means that A equals 7.47. Next step, we need to calculate the dt minus C, which equals 21.5 minus 7.47. This 21.5 minus 7.47, which is going to equal 12.7. So now we can calculate eta of the steel, which equals the dt minus C over C. So it is going to be 12.71 over 7.47, all multiplied by 0.003, which is going to equal 0.00433. This means that the eta of the steel, it is more than 0.002 and it is less than 0.005. So phi is governed by the equation of 0.48 plus 83 multiplied by epsilon of the steel, which is 0.004338. So it is going to equal 0.84. So this is it for our video today. See you in our next video. Thank you.